This is me doing a derivation of the Michaelis equation, which describes the kinetics of enzymes and how they interact with the substrates. For starters, we're going to have E plus S, which will give us the enzyme substrate complex, also known as the Michaelis complex, for the step 1 mechanism. And then step 2, we'll have the Michaelis complex breaking apart to give us enzyme end product. For step 1, we see double arrows because this can happen in both a forward reaction and a backwards reaction. The rate constant for the forward reaction will be known as K1. For the backwards reaction, it will be known as K-1. For the second step, since there's only one arrow, that means it's only going to have one rate constant. This reaction cannot occur backwards because there's not enough product to give us a backwards equation. And this rate constant is going to be known as K2. Next in our equation, we need to know that the initial rate of the reaction is known as V subscript 0, which equals K2 times the Michaelis complex, which once again is also known as the enzyme substrate complex. And this is written out like this. The issue with this expression is that we do not know the concentration of the enzyme substrate. We can take an educated assumption that this number is going to be low because it doesn't change, because the rate of the formation is equal to the rate of the breakdown. This is shown by another equation, which I will write out for us, which is going to be K subscript 1 times E times S, which is the concentration of E and the concentration of S, equals K subscript -1 times the concentration of ES plus K subscript 2 times the concentration of ES, which is written out like this. But in this equation, we do not know the concentration of the free enzyme E. This is because some of it is bound and some of it is not. Meaning bound is bound to the substrate, and then some of it is just floating around. Well, not floating around, but it's free. It's not bound. So we will actually do enzyme total, which will be represented by E subscript T equals E plus ES. Because if we combine our free enzyme and our bound enzyme, that will give us a total enzyme. Knowing this information, we must use it to isolate ES by substituting E subscript T in the steady state equation, which I will write out for you. So in this expression, we start off with K1 times E total minus E bound times the substrate equals K negative 1 enzyme substrate complex plus the K2 times the enzyme substrate complex. And you'll rearrange that, and after you rearrange it, you will get this equation down here. And in this equation, it will be rearranged to isolate the rate constant and then replace the constant with the Michaelis constant of Km. So when you rearrange that, you should get this equation here. And in this equation, it's important to note that Km equals K negative 1 plus K2 divided by K1. The substitute value of the concentration of the enzyme substrate complex into equation 1 should give us the concentration of the enzyme. For equation 2, it can also be called the catalytic constant, which is known as Kcat, because it represents the rate constant of the entire reaction. When we talk about this, we'll end up with a different equation that looks like this. Which is this. But in this reaction, which is this, but in this reaction, K2 will actually be substituted for Kcat. And this is because your Kcat is actually your K2 rate constant, because it's the catalytic constant in the steady rate equation. The Vmax is equal to the total enzyme concentration times the catalytic constant, which will be represented as Vmax equals Kcat times ET. And this will give us, like I said, our Vmax into the equation. And you will substitute your Vmax into the equation to get the final form of the Michaelis-Mitten equation, which will look like this. Which will equal the initial rate of the reaction equals the Vmax, which is Kcat times your enzyme total concentration. So your initial equals your Vmax times the substrate divided by your Michaelis constant, which up here we described what the Michaelis constant was when I put it right here, and I told you that the Michaelis constant was K substrate negative 1, which is the backwards rate constant, plus the second expression's rate constant divided by the forward rate constant of expression 1, which is your Michaelis constant, plus the substrate. And together, this will give you the final form of the Michaelis-Menten equation.